If you take away this metal shield, you can get down to the bare CPU die of the Raspberry Pi 5's new system on a chip, the little piece of silicon that makes this computer go. Getting the die shot you're seeing was an adventure, and I learned a lot about modern computers. By the end of this video, we'll zoom in another 1,000 times with an electron microscope. With piezoelectric probes, we can test a single 16-nanometer transistor. This is at the scale of DNA molecules, and you certainly don't want DNA interfering with your computer. That's why I was lucky to work with Kleindiek and John McMaster to get an inside look at the Raspberry Pi's silicon. But let's rewind a bit. Andrew from Kleindiek reached out after I x-rayed the Pi and said he'd love to help me probe the chip. Then, around the same time, I found a really weird overclocking bug. You could overclock past 3 GHz, but performance would stop improving. With the Pi 4, some people did get pretty exotic speeds with better cooling, but even with this water cooling block from 52 Pi, there was no way I could go faster than 3 GHz. So I asked Raspberry Pi about it. Their engineer mentioned it was because of something called a PLL. PLL stands for phase-locked loop, and it's related to the little oscillator chip that's just under the SoC right here. These crystals, or CXOs, are a critical part of every computer, even the phone, computer, or TV you're watching this on. And even a tiny Raspberry Pi has a few of these things. It looks a little boring on the outside, but here's what one looks like sliced open. You can see there's a tiny bit of quartz crystal inside. And just a quick note, this book, Open Circuits, it's awesome. Anyone who does anything with electronics should grab a copy. I'll link to it below. But fascinating as that is, an oscillator is pretty old tech. It's just a piece of quartz tuned to a frequency. With help from some experts, I'll bring you on my journey into modern silicon, all the way down to transistors. But before we get that deep, let's talk a little bit more about overclocking. Not every Pi 5 can even hit 3 GHz, no matter how well you cool it. Like, this 8 gig Pi 5 can only run up to 2.8. It crashes if I try 3. And this Pi boots at 3 GHz, but locks up when I run benchmarks. There's a term for variation chip to chip. It's the silicon lottery. Channels like LTT and Gamers Nexus covered it before. But let's say you have the best Pi 5 chip ever made. No matter what, you're never going to get it past 3 GHz. Why is that? PLLs, or phase-locked loops. We're going to get a little geeky here, but don't worry, we'll take a step back in a minute. On the Pi 5, there's a reference table called the OPP table, or OP table. That stands for Operating Performance Points. It defines a set of voltages required to run at specific CPU frequencies. Basically this. But that table is generated when the Pi's running by proprietary code running inside the Pi's chip, so these numbers are a little wonky. I reached out to Raspberry Pi and they couldn't speak to the op table, but they did tell me, and I quote, 3 GHz is the largest multiple of the 54 MHz crystal oscillator they can support. There's that oscillator again. If you look really close at the bottom of the Pi 5, you can see that little crystal is indeed 54.000 MHz. Bear with me on this tangent, because I think this stuff is fascinating. Computers like the Raspberry Pi use a little quartz crystal, remember, just like this one, but it sends a tiny bit of voltage through it. That crystal vibrates, generating a signal the phase-locked loop on the chip uses to generate the frequency the whole SoC uses to process data. And a modern chip like the Pi's uses something called DVFS, or Dynamic Voltage and Frequency Scaling, which lets it change voltages and frequencies on the fly to save power when nothing's happening. If this all sounds like rocket science, well, let's step back, back to the 15th century. Back then, timekeeping was kind of the Wild West. From sand to sunlight and even water, there was a lot of experimentation to find the best way to use physical matter to keep track of time. But in the 15th century, the pendulum won out. People discovered harmonic oscillation was way more accurate than things like sand pouring through glass. Early pendulums were accurate within about a minute per day, which was a huge improvement over sunlight, sand, or water. Clocks got better and better, and even modern atomic clocks do basically the same thing those first pendulums did. They measure oscillations. Instead of a piece of metal swinging back and forth, though, it's tiny atoms. But computers don't need quite that much precision, well, at least most of them, and someone even built a pendulum-based clock for their Apple II computer. A pendulum can be pretty accurate, but quartz crystals are accurate and a lot smaller, so that's why this tiny 54 MHz chip is on the bottom of the Raspberry Pi. The 54 million oscillations it generates every second can be scaled up by the PLLs inside the Pi's main chip. And that scaling means we can use a cheap quartz crystal and boost its frequency all the way up to 2.4 GHz. If you're having trouble with PLLs, think of them kind of like a drummer. You might have a song that's 120 beats per minute, but throw in a bunch of 30-second notes and things get crazy fast. You have this chip oscillating at 54 megahertz, and a PLL can divide that time up into smaller chunks. It only has to multiply the source signal by about 40 times to get to the Pi's default 2400 megahertz clock. But just like that drummer, the PLLs only go so far. You might wonder about just replacing the 54 megahertz oscillator to trick the PLLs into going past 3 gigahertz. Some old computers could actually go faster with this clock chipping. But the problem with that is there's not just one clock nowadays. There's DRAM tied to the CPU and things like PCI Express with its own clock. If the timings get too far off, the computer will crash. Just like if the drummer starts going off beat in a band, you run into weird bugs when the computer clocks get out of sync. As a practical example, I had a ton of issues getting the Coral TPU to work on my Pi. Eventually, we found that the cable was adding a little bit of noise, which caused the PCI Express clock to go out of sync with the chip on the Coral. Just replacing the cable fixed that issue, but one of the Pi engineers found he could also create a separate clock reference closer to the Coral, and that would also fix it. But bottom line, the current generation of Pi 5 can't go past 3 gigahertz, and heat isn't even the main enemy, like it was with the Pi 4. If you use any cooling at all, it's actually hard to get the Pi 5 to throttle. The overkill water cooling system kept the Pi at like 45 degrees Celsius maxed out. But even this passive heatsink case Editech sent kept the Pi running at 70 degrees, no fan at all. So water cooling to overclock a Pi 5? Not practical. I mean, it's not worthless, it's kind of like using a blowtorch to light a candle. But assuming we had good cooling and could go past 3 gigahertz, would it be worth it? Well, yes and no. For the fun of it, yeah, totally worth it. I mean, you're talking to the guy who built the petabyte Pi. But at higher and higher frequencies, transistors turn more and more power into heat as they switch on and off faster and faster. More heat means less efficiency. In this blog post, I found out the default 2.4 gigahertz clock is pretty much the sweet spot for efficiency. That sweet spot is partly dictated by the size of the transistors, or the process node for the BCM2712 chip. In this case, 16 nanometers. We're gonna get down to that level in a minute, but first I wanted to take a look at the silicon on a more human level. None of us can see individual DNA strands, but we can see shiny die shots. So I worked with John McMaster to look at the BCM2712 and the RP1 chip next to it. Before we go further, I have to give a disclaimer. I'm not a silicon expert. I'll link to John's Twitter and other resources below, but let's delid this thing. And right off the top, and I do mean off the top, John had issues. The epoxy under the lid is really strong. John actually had to pop a few chips apart before one of them came off clean. And after a little polishing, here's the first layer. Now, this might not look like much, but it's basically the entire I/O grid for the chip. Each of these little dots is where a tiny solder ball connects through to the chip's interposer board. That's this part of the SoC. It goes between the tiny silicon chip and the larger solder array that's exposed on this Pi 5 here. In this cross-section of the Pi 4, you can kind of see how that looks from the side. But getting back to the silicon, this top layer, or well, the bottom, since this is a flip chip design, it's all the interconnects. There are tons of little lines routing signals to all the pads. And before I start highlighting any details, just to give context, I'll fade from the top layer to the layer just under it, the top of the metal interconnects. Then there's the bare silicon, which is a bunch of layers down on the surface of the silicon wafer. And finally, here's a more colorful picture of that same thing. This progression from the top layer down is helpful for context, and I'm sharing all this on my blog too if you want to scroll at your own pace. Getting back to the top layer though, you can already spot interesting details. Like if we zoom way in over in the corner, there's a little copyright. There's also a C and a 0, and that means this is stepping C0. What's a stepping? It's like a chip version. A lot of early production runs, or tape-outs, have little bugs. You work out those bugs until you get a production chip, and in this case, it looks like it's on the 3rd revision. There are also 11 little rectangles depicting the layers built on top of the silicon, all the metal layers. But you might notice this whole thing is really yellow. That's because this layer is actually the polyamide layer. Polyamide is an insulating plastic that can take high heat and protect the metal layer below from oxidation. But John stripped that away, and what you're seeing now is the top metal layer. This is where all the silicon circuits are interconnected and passed out through the ball grid on that top layer. And looking around here, details are getting clearer. Like, you can see a bunch of little octagons. These are inductors. They filter power to certain parts of the chip, but they kind of remind me of the Omni Consumer Products logo in RoboCop. Between layers, I noticed a bunch of areas with slightly offset dot grids. Those aren't circuits, but what are they? Well, with chips getting smaller and smaller, designers add in this fill. It helps with capacitance and signal timing when there are gaps in the design. And up here in the top right corner, there are some more of those inductors. If we zoom in even more, there are even smaller inductors peeking through from other layers too. And here you can see two similar looking blocks. There are a lot of areas where there's a grid of similar layouts, like over on the left, there's another grid of 4 identical mirrored layouts. If you look closely, there are circuits peeking through from behind there. John etched away all the top layers, and now we're down to the bare silicon. All that stuff that looks like stains and cracks, that's from chemical etching to get rid of the metal. You can either polish or etch, but either way it's pretty destructive. But here, the overall chip's architecture is exposed. Again, I'm not a silicon expert, but it looks like at least the ARM A76 cores are laid out down here in this corner. Those more solid color areas are caches, the high-speed memory right next to the transistors to get data to and from them as fast as possible. And a lot of these areas around the edges are all the I/O blocks like PCI Express, HDMI, stuff like that. There's a full 12-core GPU on this chip too, and that's over in this space, but I haven't narrowed it down exactly. Also mixed in there, Raspberry Pi developed their own video decoder and image signal processing pipeline too. If you've ever seen a die shot before though, you've probably seen a lot more color. This picture's more dull because it has a uniform light source looking straight down through the microscope. But if you position lights around the die, it comes alive, like in this picture. And it's fascinating. You know why there are so many colors? Because the silicon features, those tiny 16 nanometer structures, are so small they diffract light wavelengths differently. Just like a prism bends white light into a full rainbow, tiny features on the chip change the wavelengths of light that reflect, causing this splash of dazzling color. I even have an old silicon wafer from the 80s. Back then, we weren't even close to nanometers, but even with its micrometer scale circuits, it makes beautiful colors too. But back on the Pi, you can see a bunch of different patterns depending on the lighting. We're going to zoom in like 1,000 times more though, down to the transistor level. But before that, here's a shot of the RP1, which is a 40 nanometer chip. This chip is a lot simpler, and John didn't strip it down to the base layer like the BCM2712, but it doesn't do quite as much as the 2712. It has a lot of I/O though, and you can see all that exposed around the edges. If we zoom way into the top right corner, there's a fun little Raspberry Pi pixel art logo etched in there. And at that zoom level, you can see some more of that fill again. Moving down a bit, there's another little copyright notice, and look, another C0 stepping. Apparently they were on the 3rd revision of this chip back in 2021. As amazing as all that is, a microscope can't show you the circuits on it like we could with this 80s silicon. Pop one of these on our microscope and everything's revealed. But seeing that level of detail on this 16 nanometer chip, that's impossible. Well, unless you use an electron microscope. Lucky for us, Kleinbeek has one of those. They build piezoelectric controls and software to help chip companies debug modern silicon. This 27-axis stage moves tiny probes with 0.05 nanometer resolution. They can literally move these probes around 1 atom at a time, and that's just insane. But high-end chips are getting down to like 2 or 3 nanometers, so that precision is useful. And the Pi transistors are like 5 times bigger than that, so this should be a walk in the park. But just like John, Kleinbeek also had trouble prepping the chip.
The strange thing is, what was here that when I polished it, suddenly the chip or the part of the chip went away exactly at the contact layer. So normally you have to polish and polish and polish and polish, but in this device was really different from all others I had so far.
When John took off the heat spreader on the first Pi 5, this is the result. The silicon stayed welded to the heat spreader and actually ripped right off the interposer board. That's not normal. And these issues weren't just from carelessness. Andreas was very methodical. First, he scraped off epoxy around the chip, and then he held it under hot air for a while, but it wouldn't budge. He even cut the whole package in half to get this amazing cross-section, but when he started polishing it, the die actually split right open like a book in the middle of 2 layers.
So there's a crack down the middle right here, right?
Yeah, exactly.
And then you just fold it open like a book. Right?
Yeah. I never experienced this.
But probing transistors is a little more involved than die shots. A lot of that has to do with the beam of electrons bombarding the chip. Andrew walked me through the process of prepping the Pi's SoC. After they exposed the transistor layer, they glued it to a stage with silver paste. The glue is conductive, and for good reason.
For the scanning electron microscope, the sample has to be mounted to the substrate in a conductive fashion because you're bombarding with electrons. And if it's not conductive, it'll accumulate charge. And then if the sample charges with electrons, it has negative charge, and you shoot an electron at it, that gets repulsed. And then the beam goes all wonky, and the image is it's like looking at mush.
But that's not enough. They also need to get rid of any organic compounds. To do that, they bake it on a hot plate at about 90 degrees Celsius for a while, covered with glass. They also use gloves and special tools when they touch the chip. The point is, even before they put the sample in the chamber, they want it as clean as possible. They place it on the prober shuttle with all the probes and load the whole thing into the SEM's vacuum chamber. First, they load it in through a smaller load lock chamber. Then, once it's inside the microscope's vacuum chamber, they run a plasma over everything to burn off any remaining contaminants. And finally, after clearing the gas they just created, they can fire up the electron beam. Now, this part where we actually have the chip loaded in, I've sped it up a lot, and that's because this process, because of the precision and the way it's imaged, it takes a bit of patience. It typically takes around 15 minutes from loading the shuttle until the probes are in contact with the sample. And especially since this is the first time Andreas is looking at the Pi chip, just getting oriented took a few extra minutes. But I asked Andrew, how many transistors could you possibly test on a chip in one day?
They call it like 60T, as in they do 60 transistors in a session, or 40T, or 14, whatever, they go from one to the next, to the next, to the next, to the next, until they find the one that's acting up, right? That's not performing the way it's supposed to.
So it's not like they're going to test all billion transistors. Chip makers do a few other tests before getting to this stage. They have special debug sockets, kind of like a bed of nails tester for CPUs, where they can run the full package and see what parts are failing. Then they have something called Oberch, which uses frickin' laser beams to optically test transistors.
Optical beam induced resistance change.
Interesting.
The optical beam is the laser, and then you induce a resistance change and you see where it is, and it tells you, okay, I have to go look at this area more precisely.
They even have other methods using EBIC and EBAC with the electron beam to get even more precise before they switch to individual probes. Anyway, we're finally getting to the stage where we can probe a single transistor, and at this point, Andreas pulled up a different screen to show voltage sweeps while he tests the contacts.
In order to determine which transistor is the one that's failing, you run these IV curves, which you saw, where you have these kind of families of curves, and each curve is a different gate voltage, or can be. That's one of the typical measurements. We have, you do a voltage sweep and record the current response at, let's say, a gate voltage of 1 volt, and then 2 volts, 3 volts, 4 volts, whatever. It's like 0.1, 0.5, 0.8, and 1, or something, whatever. It depends on the device. And then the person who designed the product, he knows, okay, this transistor should yield this much current at this gate voltage. Right? And if it doesn't, well, then that's a problem.
It's a process that requires a good amount of focus, but Kleindiek makes their controls better even while chips get smaller. And if you weren't already amazed, these probes are measuring electrical voltages in femtoamps, and apparently just the box that does that costs like $80,000. They also have Peltier stages for thermal testing. They can heat up and cool down chips they're probing. That's extremely helpful because a lot of failures only happen in the most extreme conditions. And like everything else in this setup, Peltier stages aren't that cheap either.
So how many years until something like that could come into my house?
A focused ion beam? A long time.
You have to apply for a job at a company which already has these things.
Yeah, exactly.
Yeah, or find somebody to sponsor a new lab for my office.
Yeah, but that's like a whole, that's just a whole lab, and that's a whole, whole room of pumps and racks of, controllers and everything. It's really a big deal. Actually, if you go one step further to TEM, transmission electron microscopy, those are these huge microscopes that are like, 2 stories tall, and these huge boxes, and they actually build buildings around them. Like I've been to universities where they're saying, oh, we're building a new building to fit this microscope inside of it. So you first, before you order the microscope, actually call the contractor.
Beyond debugging, they can even etch away material while they're probing to find shorts across layers. As chip designs get more three-dimensional, that's a huge help. And transmission electron microscopy that Andrew mentioned lets us see inside the silicon structure, not just the surface. This stuff is incredible, and it's not just useful for chips. There's tons of scientific research enabled by the tech in these modern probes and microscopes. Now, before I move on, I wanted to highlight a video Der Bauer did a couple years ago. In his video, they analyzed a 7nm transistor, so about half the size of the Pi 5 transistors. I'll link it down below if you want to see more. The problems Kleindiek helps diagnose are often short circuits, opens, or leakages in the tiniest circuits humans have ever made. Scaling way up to human scale, where you see this whole computer, hopefully this video gives you some idea of what's going on deep inside the silicon of even a humble little Raspberry Pi. It's also helped me understand more about why overclocking has limits, especially on the Pi running relatively larger transistors. In the future, if Broadcom does a die shrink, maybe they could push this chip past 3 GHz. Smaller transistors generate less heat. But going smaller costs more and needs to be validated all over again, so it's a trade-off. One bit of tech that doesn't shrink quite as much, though, are these little clock chips, the oscillators that give our computers a reference frequency. And did I mention the quartz crystal inside here? It's piezoelectric too. It operates on the same physical principle that those probes use to position themselves within an atom of space. Modern silicon is amazing. I've said before, though, I'm no expert, but one way I can start learning more is through this video's sponsor, Brilliant. From beginning computer science to physics, math, and even quantum computing, there are courses to level up your skills. Their courses could help you advance your career, or if you're like me, brush up on things you never got to learn in school, like large language models. LLMs power everything from autocomplete to ChatGPT, and if you want to understand how they work, you should take that course like I did. Learning the basics is important for any engineering or tech work. To try everything Brilliant has to offer free for a full 30 days, visit brilliant.org/JeffGeerling or click on the link in the description. Use my link and get 20% off Brilliant's annual premium subscription. Until next time, I'm Jeff Geerling.